Continuing on with class number 4, here is like the hand waving part, a lecture, what have you, of dealing with path coordinates, also called tangential and normal components. As mentioned before, in this coordinate system, the coordinate system is based on the orientation of the particle on a path, where the tangential coordinate unit vector is tangent to the path, which means that it's aligned with the velocity, because remember, the velocity is always tangent to the path. And so the other coordinate system, the other coordinate unit vector is perpendicular to that and pointing towards the center of curvature. All right, so they're orthogonal. That means that they are they are perpendicular to each other. They're normal, right? That means we have a perpendicular coordinate system, and the normal one, by definition, then has to be perpendicular to the tangential one. For a velocity vector, then, and all we need is really just the magnitude of the velocity, which is also known as speed. So speed times that tangential unit vector gets us the velocity. And I'm reminding you down here. Right? All right, so taking a look at my notes and the important things that I wanted to say right here. All right, so here is the acceleration now. All right, so here was the velocity, just v, it's a scalar, the scalar value of the speed. That could be positive and negative, by the way. Well, let me be careful there. Depends how you draw your coordinate axis, right? If for whatever reason you decided that this was going to be the direction, but it should probably go in the same direction, right? I got to be careful of what I said right there. All right. So anyway, we have a magnitude, and then the unit vector serves as the telling us the direction. Now we have for the acceleration, we have two terms, not just one. We have the tangential and the normal. The one in the tangential, that acceleration is just this acceleration you would normally think of, right? It's the change in speed. Like you put your foot on the gas pedal, aka the accelerator, and you go zoom zoom, you go from one velocity to a larger velocity, and now you've accelerated in the tangential direction, right? Or just in the one-dimensional direction. But if you're going around a curve, you start to feel pushed to the side, right? And you start to wonder, like, wait a minute, shouldn't it be going outwards? Shouldn't I be accelerating outwards? And let me find my little die-cast Mustang. It helps me to explain things. Okay, so we have our little die-cast Mustang right there. It's a 1964 and a half. Or does it say that right there? Yeah, 1964 and a half Ford Mustang right there. And we got a little dude inside. He's a little skeleton, little Lego skeleton guy. I think he's from like Pirates of the Caribbean skeleton Lego set. Right. Anyway, he's inside, and he's going for a ride. Right. So, in the tangential direction, that's just him going faster. But if he starts to go around a curve, right? So he's got a curve. Think about, when he starts, right? So he's about to go around a curve. And he's starting before the curve starts, this is the velocity vector that he has. He's coming through. And just as he starts to get to the curve, well, let's see, what I like to ask is, well, if this was the I and j, what would be the value of his I velocity just before he starts? It would be 0, right? But now he gets a little ways into the curve. Maybe he gets to right there, and there is his velocity. But now if we were to put it in terms of I and j, let's just move the I and the j over there. Now, what is his magnitude? What would his velocity be? His velocity would have, these coordinates right there, right? So he had 0 in the I direction, x direction, when he's just before the curve, but now he's a little ways into the curve, and now he has some. Now he has some velocity in that direction, right? So he must be accelerating to the left. He's accelerating, and if you kept doing these smaller and smaller, you would see that the acceleration, so that's the change in velocity. He has to have a velocity component going to the left in order to make this turn. Otherwise, just like Newt Dog, you would go driving off the cliff. He's got to have an inward acceleration in order to go around the path. That is the, oops, I think I had the wrong one there. That is this acceleration right there. And that's centrifugal or centripetal. I don't know which one we might call it there. So this one is due to the change in speed. This one is due to the change in direction and is equal to the velocity squared divided by the radius of curvature. And that could be like some really, really big value, right? So we would like maybe have to have a really big compass, and it might be really far away depending on how wide this curve is right there, right? So it could be a narrow curve right there, right? So you have that radius right there. It depends on the curvature of the thing, how big it is. But it also depends on the velocity squared right there. So remember that this v is speed. This rho is the radius of curvature. And this is the tangential component. And this is the normal component. And the tangential is due to change in speed. And this is due to the change in direction. And hopefully you believe because of the little Mustang and little skeleton dude, right? Now the reason why you feel like you're going to the outside is that the car is pushing you around, right? So if you start to kind of go to if you on this curve right here, the skeleton wants to keep going straight, right? He wants to keep going straight, but you're telling him, but you're starting to curve, so you start to get forced to the outside because, come on, so we're playing with Legos. I'm a grown man playing with Legos on a video I'm posting, right? Should be on Snapchat or something, right? No, that's not how that works. Not Snapchat. No, what is it? Instagram? I don't know what the hell people. Anyway, so like, let's say he has the doors open, right? And he's going around the curve. He wants to keep on flying. He wants to keep on flying, but the door is closed. And the door says, no, you can't keep going straight. You got to go to the left, right? You got to start turning. So he's feeling like he's getting pushed up against the door because he wants to keep on moving. So that's why you think acceleration is going outwards. Acceleration is actually going inwards, and you're just feeling like the reaction force of the car telling you you got to go inwards. So that's the explanation for why people get it confused, or why it's hard to accept that acceleration is towards the center. So other things that notice that these are perpendicular to each other, that the magnitude right there is that, and this is the magnitude. Here's the magnitude of the acceleration is just the sum of the squares of these two components right there. And I have the derivation now, quick and dirty derivation. So here again, once again, by the way, here's the here's Newt Dog running off, like he's tangent right there, and so he's going off tangent to the path, but he just keeps on going. He needs to have acceleration towards the inside of this curvature to stay on the path, but he doesn't. So that is what this cartoon is trying to display and trying to stick in your mind. You could also use the little Mustang and the skeleton, and maybe he's more memorable than my little drawing, but I mind. Hurt my feelings then. You don't like my little drawings. Okay, so the book covers this, but I will do a little brief thing. All right, so in tying into what we did in class 3, where we were talking about the derivative of vectors, remember that this is the velocity vector. It's a speed times this unit vector. So because of the product rule, we have to take the derivative of this and the derivative of that. So when we take the derivative of v, that's just dv dt, right, times the original product rule, right? But now we have to have v needs to be multiplied by the derivative of this. So we have to kind of figure out, how do we take the derivative of a unit vector, and what would it mean? Well, we go back to this idea of having 2 points right there, and here's the initial unit vector in the tangential direction. Here's the unit vector at another time, at another point, right? So we move from P to P prime, and now we have a new unit vector, right? They have the same magnitude, by the way. So, I'm trying to answer, what is this? Like, what is that right there? We note that, like, if we were to, let's see, I think this note right here needs to come down to this guy right there, right? Yeah. Oh, okay, I see. All right. If we take this vector right here and we move it down, and there's no reason why we couldn't, move it down to over, say, I'm going to try to draw it out straight. If we move it down to, like, right there, right? So this is ET prime. We would see that the difference that had been made between those two would be this right here. That would be delta ET, right? That's just, here's the change in the unit vector. The unit vector was here, is here, so if you bring these two together, you find here's what the difference was going to be. But if you kept getting smaller and smaller in here, you would note that this would start to point towards the center. Right? So as this changes with respect to the angle that's in there, right, the angle that's formed between there, if that angle starts to get smaller and smaller and smaller, it starts to get more and more perpendicular to this vector right there. You see what I mean? Like, watch, this starts to get smaller and smaller and smaller. That means that this thing starts to straighten more out and becomes more and more perpendicular. So we can say that the derivative of this ET with respect to a change in angle is equal to EN, because it becomes normal to it. So like we almost, here's the point where we start defining what EN is. What is EN's perpendicular, because this thing got smaller and smaller, right? So I take back what I said about down here. But now, this is DET d theta. We need it dt, right? So how do we do that? Well, now we use the chain rule and apply that to here. And one thing that's going to help us in that chain rule is figuring out how this arc length right here. Right. So let me back up a second. If we want to, one thing we could find, right? Okay, so let's say what this arc length delta S is going to be right here between the 2 points. It went from P to P prime. One way we could write that is this is going to be the radius of this times the angle in radians, right? That defines an arc length. So by saying that, we can say this right there, that we just divide that arc length by that rho, and that'll give us this relationship. And therefore, we could say, as it got smaller, we could say d theta ds, I'm just doing a little bit of manipulation here, is 1 over rho right there. You see that? Now we just say we divide that delta theta by that delta s, and we get 1 over rho. Okay, so when doing this chain rule and attempting to get this theta into a dt right here, we could go through this with the d theta ds, what we just had right there. But now that means we have dt ds, and we don't want that. So instead, let's have ds dt. That'll give us the ds's, right? And these things all cancel out, and that'll get me my det dt, right? Well, note that right there is equal to the velocity, right? ds dt, that's just the change in length divided by the change in time. So what we have is en. So we have this guy right here that was up here, now has become this. So if we stick that back up in, we'll see there's already a velocity. So we have velocity and a velocity. So we have v squared over rho, and therefore that is the normal acceleration, right? So there's a quasi-differential, derivation. I lost the word derivation. So there's a quasi-derivation to try to like convince you this is the correct equation for the path coordinates acceleration. And it's all about the fact that we had to do this this product rule, right? We had to take not only the derivative of this velocity, the speed right here. So this is the change in speed. We also had to take the derivative of this changing orientation of the tangential unit vector. And we had to do some manipulations in order to find what that was going to be. Down here is where we had made it. But we were able to use this chain rule. And so we used the product rule and the chain rule all in one derivation. But here is the thing, and this is on our equation sheet, so we could just memorize it and put the rest of this out in our head. But now we knew where it came from, so it has like some more meaning to us. So I'm going to do an example in the next video.